work is evaluating code summarization techniques, a new metric, and an empirical characterization. I would like to mention also that this work was conducted in collaboration with Mastropaolo from the University of Sugno, and now is currently under revision at TIXI at the second cycle deadline after we got basically asked for implementing some changes. And with all that being said, let's dive into it. So I would like to start this seminar by stating something that should be pretty much clear to each one in this room, that is, documenting the code is extremely important. But this activity is not this great, right? I mean, it's time consuming and oftentimes developers neglect to document the code. But on the flip side of this, I mean, we acknowledge that commented code is much more understandable as compared to non-commented code. So much so, the very first evidence of the importance of having commented code in terms of code understandability traces back to this ICSI paper in 1981. So quite a few time ago. And since then, also other developers, of course, started working on this topic. And in particular, in this work by Steadley colleagues, the authors found out that developers do not always carefully comment code or update existing code comments in response to code changes. And as you can imagine, the consequences of having these inconsistencies between code and code comment has been explored over the years. And again, researchers are keep exploring this over and over again. But here there is something, because despite the researchers pointed out to those inconsistencies, there is a thread of research that makes massive usage of these code comments that might be of low quality. And I'm talking about techniques that can produce documentation for code components. One in particular being code summarization that we will be using in this seminar as a running example works as follows. As you can see, we are in the Java context because we run this investigation using Java methods, precisely the Java programming language. In the middle, we have a deep learning component that will take as input the Java method and as output will produce the summary for this Java method. Now, keep in mind that in the context of Java, when we talk about the summary, the code summary for a specific Java method, we are referring to the very first sentence of the Java doc, meaning everything that comes before the very first dot. We can take this and we can consider this as a code summary. Once we have the summary automatically produced by this deep learning model, then we can evaluate the summary. And oftentimes, we, researchers, use a very strict measure to evaluate how good the model performed. And I'm talking about the correct prediction rate. By correct prediction rate, I mean if the model produces output something that token by token is exactly equal to what previously was written by the developer, the ground truth, so what you can see here on the left side. On the other hand, if the model actually did not produce the correct summary, in this case, we can talk about wrong prediction. However, researchers actually realized that this is a measure too strict in order to evaluate these specific approaches. So they started using metrics from the natural language processing field, such as the BLEU score, the ROUGE score, and the BERT score. In general, we can distinguish between these metrics in two categories. We have word-based or overlapping-based metrics and embedding-based metrics. There are many more that we have used in our investigation. Here, just to get you a little bit of an understanding, the very first two, the BLEU score and the ROUGE score, fit the word or overlap-based metrics because they are considering overlap of tokens between the ground truth, so what the developer has written, and the prediction. While metrics such as BERT score that instead fit the embedding-based bucket, in this scenario, the first compute vectors using embedding technique. Later on, these vectors are projected into the vector space, and some sort of similarities between these two vectors can be computed, such as the cosine similarity rather than the Euclidean distance. So if we bring back our example and we compute the BLEU score here, we found out a BLEU score of 0.26, meaning that is very low. So what the model produces is not quite accurate. And to some extent, this is fine. But there is something here that I would like you to notice, because when we use natural language, we can express different concepts. The same concept using different words. So if we take a look at the very first code summary, this is what the model produced as a summary for this method. The very first summary says, reads the content of this source as a string. While what the model was supposed to predict, what has been written by the developer, is get the textual information from this source and represent it as a string. Now, here it's a no-brainer that these two summaries are semantically equivalent code summary. And yet, if we compute the BLEU score, this turns out to be like 0.21, meaning that these two summaries are not related each other, and this is not correct in a way, because I mean, if we think about this, here there is something that is going on, because we are evaluating code summaries, good, but where is the code going in this evaluation pipeline? I mean, why the code is disappearing, and why we are not taking the code into account when evaluating code summarization techniques? So this is what we actually observed, and what we propose to mitigate to some extent this issue is to align summaries to code components, in this case summary to method. As you can see here, our goal would be to associate in a way the correct summary, the one that you can see on the top, with this method, being that one, the correct code summary, meaning something that documents that method. And at the same time, we also would like to push apart wrong summaries from this method, because we know that this one, the summary right here, actually is not a good fit for documenting or to summarize this method. And a technique that would serve this purpose is based on contrastive learning. And let me illustrate why we decided to use contrastive learning for this specific case. Now, here we have these black dots are the methods. These green dots instead are the correct summary for that method, while the red one are a summary that actually, as I said before, are not good candidates for that specific method, meaning that these summaries does not document that specific methods. Using a contrastive learning technique, what we can do is to project these triplets into a vector space, and we want to maximize the distance between the method and the wrong summary, and at the same time minimize the distance between the method and the correct summary. This is a way to capture, if there's any, or to align, if you wish, correct summary with method, and at the same time wrong summary with methods. To this end, we relied on a dataset previously released in the BLEU benchmark that features several datasets and models when it comes to deep learning for software engineering. This was a curated dataset that includes 180,000 pairs of Java elements, where each pair includes the code summary that documents the associated method. Then, to create these triplets that are the input of the model that we will be training, we randomly select for a given triplet, we randomly select the code summary that it's very likely that does not document that specific method. Once we came up with the dataset, we relied, as mentioned before, on a deep learning model Just for reference, this is a BERT-based model that has been trained to bring together summary and method that are in a way correct, meaning that that summary, again, is a good candidate for documenting that method, and pushing apart summaries that means nothing with that method, the one that we are considering. Once we train the model, what we have is our metric that will take as input two elements, specifically the prediction and also the method. We feed this element to the model, and as output, what we obtain is a value that ranges between -1 and 1. With the higher, the better, meaning that the higher the value, the more close is this summary to the method. In order to evaluate SIDE, this novel metric that we are suggesting, we measure two different things: whether SIDE can effectively capture new dimensions where actually state-of-the-art metrics fail, and the second aspect that we measure is whether or not SIDE allows for a more effective representation of the developer's evaluation when it comes to the quality of the automatically generated summaries. For performing this evaluation, we needed to rely on another dataset, this time presented in this FSC 2021 paper by ROUGE and colleagues. This dataset includes 5,000 human evaluation of automatically generated summaries in terms of conciseness, that basically assess the degree to which the summary contains unnecessary information for documenting that method, the fluency, that evaluates the smoothness rate in the generated summary, and also the content adequacy, that instead measure the extent to which this summary lacks information needed to understand the code. Each one of these measures was expressed in the range 0 to 5, also in this case, with the higher, the better. Higher value, better was the quality perceived by the developer. These three measures represent the dependent variable of our investigation, while as for the independent variable of our investigation, we considered SIDE, of course, the metric that we are proposing, word and overlap-based metric, and also embedding-based metric, accounting for 13 metrics overall that have been investigated. At this point, by using the dataset by ROUGE colleagues, we can start computing the value of these metrics. So for the state-of-the-art metric, actually, we only needed the prediction and the ground truth of that was released in this dataset. Instead, for SIDE, we need the method in this case, because as I said, we want to bring the method into the evaluation pipeline. So we take only the prediction, but we take the method too. Again, as explained before, we give these two information as input to the model, and then we expect the model to produce one value that ranges between -1 and 1. For the very first analysis, so that is when we try to understand whether or not there were dimensions that our metric can capture in comparison to the state-of-the-art metrics, we run a principal component analysis with the goal of capturing the variance and covariance of this metric that are expressed as a linear combination. We observed that as for the very first principal component, 55% of the variance is captured by either the BERT score or the ROUGE score. In other words, no matter which metric we use, we're good to go with the BERT score or ROUGE score. We know that we can capture 55% of the variance described in the dataset. As for the second principal component that instead captured 16% of the variance, here what we found out is that only SIDE actually can capture this dimension. I mean, no other metrics got close to what we proposed to SIDE. Another cool aspect that we observe is that if we look at the cumulative proportion of variance for the very first three metrics, 80% of the overall variance is captured just by using three metrics. Concerning instead the second aspect that we investigated, here we relied on an ordered logistic regression model for each of the three dependent variables that have been used. So for the conciseness, what we observe is that there are 38% higher odds to observe a unitary increase in the conciseness, and this would result in a unitary increase of the value of our metric. The second one, instead, the one that you see in orange, was the second best performing one. For the fluency, we observed 28% higher odds. Instead, for the content adequacy, the odds were even higher, 62%. Now, let's get rid of all this math and let's see from the practical point of view, what does it mean? Here, we have an example reported from our paper, taken from our paper. On the top, we have the method. Then we have the reference summary right here, what was written by the developer. Here, instead, we have the generated summary, what was produced by the model. Here, on this line, we find all the state-of-the-art metrics. We only report a few, there are many more. Here, instead, we have the results of our metric. And here, what the model, what the human express in terms of adequacy, conciseness, and fluency. As I said before, we have values ranging in 0, 5. So the perceived quality here is quite high because we have 4 for adequacy, 4 for conciseness, and 5 for fluency. While the state-of-the-art metric, almost all of them actually score very low, with few exceptions for this one and the BLEU one. But the cool thing is that if we look at our metric side, here we have 0.91, meaning that in this case, side was able to capture the, in a way, the perceived quality of the developer for this specific example. Now, all this to say what? That state-of-the-art metrics are probably not sufficient to describe the human assessment of automatically generated code summaries. And we should probably take into consideration when evaluating this technique also to bring the code into the evaluation pipeline. We propose side as a first step. This can be used, but many more metrics actually with this idea can be built on top of what we observe, that we have to take the code into consideration when evaluating these techniques. With that being said, I think that I can conclude here the seminar, so thank you for your attention.